Design of a footbridge. In this video, we will discuss the design steps of footbridge step by step. Footbridges are used uh, for railway crossings, highways, even gardens. Before starting this, let us discuss what are the different components which we have to design. Let's say these are columns and this is a design of a footbridge. So first of all, you have to go for design of platform. Let's say it's a wooden planks. Then these planks will rest on these cross girders. It can be channel or I section, whatever. Then the channel load will transmit to the main girder. Main girder will composite with these kind of trusses. So this is what we have to design. Before designing, you may have an idea about live load, what is the span, total span, and what would be the width of this footbridge. Now let us start. We will discuss design steps and parallelly we will discuss the numerical also. Let us say first we will design planks, steps for planking, and then we will have a look on the numerical portion of this part, then move further and will parallelly move further with the numerical problem also. I suggest you that it will be better for you if you write all the design steps, or you will calculate all the numerical problem at your own end also. It will be good for you. So let us start. First of all, design of planking as we discussed. Let's say the problem is like this. Design a footbridge to the following particular. Let's say span of girder. Span of girder means, when we say span of girder, it means the span of girder. This is 16 meter, 16. Cross girder to be spaced at 2 meter center to center. Cross girder means these cross girders 2 meter center to center. Clear working width between main girder. It means this one is for walking. Clear walking, that is 2.5 meter. The live load, it is given 4000 Newton per meter square. Then flooring, timber planks. Flooring means on the cross girder you can have an option about flooring. In this case, you have to go for wooden planks as we discussed earlier. So let us start with your first step. First of all, span is 16 meter, girder cross girder spacing 2 meter, live load 4 kilonewton per square meter. This is all we know so far. Now, first step will be design of planking. Now, how to start design of planking? Come here. Sorry. Before starting this step, very first step, just keep in mind the design of plank will be for 1 meter void strip only, as we have designed the slabs in your docks design of concrete. Now, first of all, adopt suitable plank size. Suitable plank size will depend upon what span of cross width and thickness. So you have to go for decide the thickness. Then, according to thickness, you need to calculate total load. For plank platform, how to decide? One is live load. It has been given to you, or you will decide earlier. Then dead load. Dead load will depend upon the density of the plank. And in the case of footbridge, most of the cases impact load is 0. So no need to calculate impact load. You just add on live load and dead load and calculate maximum bending moment WL square by 8, maximum shear force WL by 2. L is span and W is total load. Now move further. Check. You have to go for 3 checks. 3 checks mean, you say 3 checks. One is bending stress, then second is permissible shear stress, and third is deflection. Now keep it in mind, if you are talking about timber planks, permissible bending stress for this case is 10 Newton per millimeter square, and permissible shear stress is 0.8 Newton per millimeter square. It means whatever stresses are induced due to these bending moment and shear forces must be within the limit of these two. Now, how to calculate? First, we will calculate bending stress. Let's say first step, this one, equating the moment of resistance to maximum bending moment. The formula 1 by 6 FBD square equal to maximum bending moment. F is bending stress which you have to calculate. Maximum bending you have calculated already. Then B and D. B is 1000 millimeter. D is the thickness you will choose. Then there will be F, bending stress. If bending stress is less than permissible, then it is safe. The same case in shear stress, that is S upon BD into 1.5. This is nothing. This is load upon area. So maximum shear force upon BD into this one is factor. So if permissible shear stress is more than this, it is again safe. Now third check. Check for deflection. Permissible deflection will be more than maximum deflection. So how to calculate this? Permissible means span by 325. Span is length. Then 5 by 325 WL power 4 EI is maximum deflection. W is load, L you know, E is modulus of elasticity. In this case we are using wooden planks, timber. So it will be 1 into 10 raised to power 4 Newton per millimeter square. I is moment of inertia BD cube by 12. So if this is satisfied, then deflection is also safe. Now let us solve design of planking according to these steps for that particular numerical which we discussed in starting. Now how to start this? Sorry, design of planking. In this case, as we discussed, the span is 2 meter only. This span is 2 meter only. Now try, you can have an option to decide the thickness of the plank. 60 mm planks we are going to use in thickness with the 8000 Newton per meter square. That is what we call this density. Okay, anyhow, so dead load can be calculated as 60 by 1000 into 8000. It will be 480 Newton per meter square. Total load 4000 Newton per meter square already given. So total load is 4480 Newton per millimeter square. Let's say we are considering 4500 Newton per meter square. Now maximum bending moment WL square by 8 as we discussed. W 4500 to L. Each and everything is in meter and Newton. So as we discussed earlier, we have to consider this as a 1 meter. So that's why we are taking this 8000 Newton per meter square, not meter cube. Now check 2. Equating the moment of resistance to the maximum bending moment. That's as we discussed earlier. This is 1 by 6 FBD square. So you calculate F, B and D. You have already decided about B and D as B is 1 meter 1000 millimeter, 60 millimeter, and bending moment we have calculated. So it will be F 3.75 Newton per millimeter square. Permissible bending stress as we discussed, will be 10 Newton per millimeter square. So it is less than that. Safe. Now again go for shear. Maximum shear WL by 8. Then maximum shear stress 1.5 into maximum shear force upon BD. How to calculate? Maximum shear force 4500. B 1000. 60 is depth thickness. So it will be 0.113 Newton per millimeter square. So it is also falling within the limit, as we have discussed that these two conditions must be fulfilled. So in this case, permissible shear stress is 0.8 Newton per millimeter square. So it is also safe. Now check for deflection. Maximum deflection, as we discussed, this is 5 by 384 into WL power 4 EI. W is 4500 Newton, L 2 meter, E as we discussed for the timber, this is 10 raised to power 4 Newton per millimeter square, I BD cube by 12, When I say BD cube, B is 1000, D is 60 mm. Permissible deflection span by 325, span is 2000 for the particular span of what we call this the flooring. So maximum deflection is occurring, this is 5.2 millimeter, but permissible deflection is 6.15 millimeter. So permissible deflection is more than maximum. So it will be safe if we provide planks of 60 mm thickness in a given portion. So this is how we have to design this planking. So now step number 2. In step number 2, you have to go for a design of a cross beam. When I say cross beam, now we have designed these planks. The load will come on these planks. These planks will transfer the same load to the cross girder. These are the cross girders, right? So now the second step is how to design cross girder or cross beams. Design of cross girder. First of all, you have to calculate total load which is coming on the cross beam or cross girders. First, the load is coming from flooring, and second load which we have to add, that is the self weight of cross beam. Approximately you can have an option at 300 Newton to 500 Newton. Then according to load, it will be WL by 8 maximum bending mode, factored bending mode, and according to this bending moment, which is factored multiplied by 1.5, you have to calculate plastic modulus section. So plastic modulus section will be moment upon Fy into gamma m. Gamma m 1.1, Fy it will be given in your problem, or you can have an option to decide your steel type. This is, let's say this is 250, then a moment. Now again, according to this ZP, you adopt suitable section from your steel table. Steel table is giving different sections according to different section plastic modulus. So from steel table you can have an option to choose any type of suitable section. Then after adopting this section, you have to go for check for shear. So maximum factored shear will be W by 8. Then design shear, it must in this case design shear must be more than your factored shear. So here in this case, design shear will be Fy upon under root 3 comma m into h into Tw. H and Tw is the height and thickness of the section. So if the criteria is, this is a criteria which you have to follow in, if it is satisfied, then your crossbeam section is also safe. Now come with our numerical problem. So in this case, clear width of footway, as we discussed earlier, it was 2.5 meter. Now let us see center to center distance between two lattice girder means, if now check carefully, if you have to put the clear width 2.5 meter, so it means these two girder have to set more than 2.5 meter, then only you can have a 2.5 meter clearly. So let's say add 0.3 meter, so it will be 2.8 meter. Load transmitter to one girder from flooring, we are considering only one girder, so it means 2 into 2.5 into 4500. 2 into 2.5 means the coming load was 4500 Newton per meter square. So what we are doing now, this is 2.5 and here it is, sorry, 2.5 and 2 meter. So now this is 22500 Newton. It was Newton per meter square, now meter into meter. Now approximately weight, as we discussed earlier, it will be 300 to 500 Newton. So we are considering 300 only. So total load on crossbeam, that is calculated easily. Maximum bending mode WL by 8. W is total load we have discussed, calculated. L is 2.8 So bending moment and factored by multiplied by 1.5. Then plastic modulus m upon fy into gamma m. Each and everything has been calculated. Now this will be Zp. So when you check your steel table, so suitable section as per this much of Zp, that is ISLC 125. ISLC means channel of width 120, depth 125, which is Zp 65.45 10 raised to power 3 millimeter cube. Now maximum shear force which is factored for this particular one is W by 2 into 1.5, so calculated already. Now design shear strength, that is Vd Fy upon under root 3 gamma m into H into Tw. Now how to calculate this? Fy 250 under root 3 1.11, then H is 125 mm. 4.4 is thickness of the web for that particular channel. Let's say this is our channel like this. This is 125, and here it is, the thickness is that we call this 4.4. This is what we are talking about. Now, as we discussed earlier, that a design strength must be more than this one, so Vd is more than this one. So it is okay if we are using ISLC 125 as a cross beam. So now so far what we have designed, we designed these planks, we designed these cross girder. Now this is the time to design this main girder with help of this truss. The step number 3. Design of main girder and truss. In this case, total load on truss, it will be dead load of truss, which you have to assume earlier, then load from the cross beam which is coming. Now how to start this? First of all, you have to choose the type of the truss, then calculate forces in all the members with the help of enforced line diagram, then design the member according to these forces which has been calculated with the help of ILD, the tension and the compression. So let's say the member is in tension, so it will be tension member. Member in compression, it will be compression member, and design will be differently chosen. Now, before starting this portion, this is the final portion, we will discuss this much of the portion up to ILD forces of this truss in our numerical. So step 3 is design of main girder truss. Now load is coming from cross beam. Total load coming from cross beam will be divided by 4. 4 means we do have 2 trusses here, and it must be per meter, so divided by again 2, so it is 5700 Newton per meter. So weight of one truss can be assumed at approximately 400 Newton per meter. So total is 5700 plus 400, 6100 Newton per meter. Now go for analysis of the truss. Let us adopt a truss type like this. The total length was 16 meter, which is given. Cross beam spacing also 2 meters. So 8 panels at 2 meter each equal to 16 meter. And let us, the height is 1.5 meter, which you have to decide. Then put a name of bottom joints L0, L1, L2, L3 up to L8, and for upper U0, U1, U2, U3 like this. Now first of all, design of different members. Before this, going to design, we can have a pattern like first we will go for top chord, top members, then bottom, then vertical, then diagonal. If you design U0 to U4, so it will be automatically, then you have a forces with a mirror image from U4 to U8. So no need to design this. You have to analyze a 50% of the truss at least. Now, before starting this, first of all, top and bottom code. So first of all, top code, with the help of ILD, we will discuss in a very short manner how to design ILD. So first of all, U0, U0 and U1. So top code U0, U1, first member. Now height of ILD will be A vector L minus A upon L into H. In this case, when you say top chord members, U0, U1, U0, U1, A will be the distance of opposite side member. Opposite side members are bottom chord on its right side. So it means U0, U1 have an opposite member, L0, L1, and the right side is L1. So this is A. Okay. L 16 meter, H 1.5 meter, right? So put all the values in the formula. So it is 1.17 units like this. So triangle will be like this. Is it clear? Now it will be more clear with U1, U2, U1, U2. So now see how to design with the same pattern. The formula is same. In this case, L is again 16 meter, H is 1.5 meter, E. So as I said earlier that A is U1, U2. So opposite one is L1, L2. So the distance up to left joint. So left joint is L2. So 2 plus 2. So it is 4 meter. So it is 2. So easily calculate 2. So according to this formula, we can have an option to calculate all this U2, U3, U3, U4. All the members can be calculated for the top code. Now go for bottom code. When I say bottom code, only difference is when you go for bottom code, let's say L0, L1, then again for A, you have to see your opposite one. Opposite one is U0, U1. In this case, when you are talking about bottom code, in this case you have to go for a left side of the joint. Left side joint is U0, U0. So A is 0, no distance. So it means if A is 0, the ILD is also 0 for L0, L1. Then go for the formula AL is same formula. A is 0, which each and everything is 0. Then go for L1, L2. In this case, A is 2 meter and it will be 1.17 units. How it will be 1.17? A is 2. When I say L1, L2 and go for opposite one, left side is U1 for L1, L2, U1, U2, left is U1. Now A is this much distance, it is 2 meter. So this is how you can calculate all these IRD diagrams. Now go for the vertical one. First of all, before starting that, we will discuss how to calculate the forces from this ILD from bottom and top code. How to calculate forces. Now, as you know very well that the deflection is like this. So bottom members are in tension and top members are in compression. Now forces in member top chord and bottom chord. Top chord are in compression. How to calculate force in member? It will be area of ILD into load intensity. Load intensity is what? Load intensity which has been calculated earlier. It was 6100 Newton per meter. Area of ILD will be, let's say we are talking about U0, U1. So area of ILD is 1 by 2, area of the triangle 1 by 2 into 1.17 into 16. 1 by 2, 16 into 1.17 into 6100. So as we know, all the members are in compression. So you can have a calculation, an option to calculate all those forces according to same formula. you have to choose the member which is under maximum force. So for that particular one, you have to design the member. The same will be following bottom code also. Bottom code in tension, this is the only difference. So you can calculate all those forces. Now go for vertical members. Now how to go for check this vertical members? In vertical members, all the members are under bending. So it will partially in tension and partially in compression. Let's say first we are talking about U naught, L naught. So U naught, L naught, that end member is on the support. So here it is simply 7 by 8. How to calculate 7? This is height. How to calculate? Let's say the one unit is acting here, one unit is acting here. So you can calculate easily what about this portion. So let's say similar triangle 1 by 16, 1 by 16, xy 14, xy 14. So here we can calculate 7 by 8 easily. If you have the area of this triangle, you can calculate your forces also. If it is positive, let's set a positive and the compression. Then U naught L1, U1 L1. So in this case, put one unit here and one unit here, and this member will be in bending. So it will be 6 by 8 and 1 by 8. The same 1 meter, one unit and 1 unit. So how this is how we can calculate. Now maximum compression and maximum tension can be calculated separately. Let's say the area of this triangle is in compression and area of this triangle is in tension. So this can be easily calculated. Now diagonal members. Diagonal members will be calculated according to this U naught L1. So only difference is like cos theta multiplied by cos theta. It will be here, it will 1.1 1.46, and let's say this portion is cos theta 1.5 by 3. So you can easily calculate this much. So here again not one unit, this is 5 by 3, this is 5 by 3 resultant. So you can calculate all these. So now the task is to calculate maximum forces induced in different members. Now how to design a truss according to these members. To design the trusses according to these members, you have go for the steps again. Let's say we are talking about tension members. First you have to propose your suitable section. According to suitable section, this has to design with two different things. One is design tensile strength from yielding concentration. The formula is gross area into Fy into gamma m. Then design of tensile strength from rupture concentration, alpha area net area Fu upon gamma m. So the least of above two must be more than factor tension force. What does it mean? Whatever the forces which has been calculated according to ILD, that force has to be less than the tension member's capacity. Same in compression member. First adopt suitable section. It is very easy. And you calculate your slenderness ratio L upon R. According to slenderness ratio, go for a table number 9 and IS 800 2007 and calculate FCD. Then FCD, according to FCD, you can have a check whether your section is safe or unsafe. So we will discuss all these members. As we know, the top code is compression. So top code will design as compression member. Choose a member which has maximum force. Let's say the member has a maximum force is 1303009 30 Newton, factored multiplied by 1.5. Length of the member we know 2 meter. Proposed section is here two angles 60 by 60 by 8. Now with the help of steel table we can have gross area and radius of gyration. So now for this particular one we can calculate slenderness ratio. This is L by R. Again, design compression stress to the slenderness ratio FCD from steel table, table number 9, IS 800 2007. FCD is 114.84 Newton per millimeter square. Now, design compressive strength will be, as we know, the load is area into stress. Stress we calculated, gross area we have from steel table, so it is 205793 Newton. This is what the capacity of your proposed section, and the load is coming on that particular one is 195450 Newton. So the capacity is more than the load, so section is safe, right? Now design for bottom chord. As you know, bottom chord is under tension, so design it as a tension maximum force. Choose a section, choose a member which has a maximum force, so factor tension. Then proposed section, let's say same proposed section can be proposed. So design tensile strength from yielding acceleration. The formula is gross area into Fy upon gamma m. Gross area calculated, coming from steel table, Fy and 1.1 gamma. Then this is also a capacity of that particular member in tension, and this is the load which has been induced. This is a force, factored force, which is induced in any member. So if this is a maximum one and the other are lower than this, so this proposed section will be okay for each member. The same manner vertical and diagonal members can be calculated. So provide, you can have an option to provide all this the same members, two angles 60 by 60 by 8 as all members, and in the last you can have design joints with your own option with rivet, bolt or welding. So in this case what we designed so far, once again, first we design wooden plank, then cross girder, then these main girder with the help of truss. Thank you very much for watching.